are you today? Good?
Yeah, she can hear you now. It's a different setup.
Yeah, okay, great. All right, so I want to start a little bit with clarifications or things I want to re-emphasize from yesterday before we move on to new material. But before I start, I would like to see if any of you all have any questions.
No questions.
Okay, great. All right, so a couple of things I wanted to emphasize from yesterday before we move on. So there were a couple of great questions yesterday about chaos. So I'm going to pull up this amazing plot from this solar system simulation paper. So the things I want to emphasize here is part of getting numerical solutions to the problem of your question in the context of the solar system, right, has to do with the accuracy of your integrator. So for example, there's this 15th order integrator that I talked about yesterday, which is this highly accurate integrator. So if your integrator is not so accurate, you will get a different final solution for your orbit than if you had a more accurate integrator. But in this plot okay, so the accuracy of your integration matters. But what's really driving the behavior in this solar system set of simulations here is just chaos. The fact that if you have slightly different initial conditions, your orbit ends up in very different places. So if you had a non-chaotic system and you were integrating an orbit using a leapfrog integrator with a couple different step sizes, if the system were non-chaotic, your orbits would end up in kind of similar places. So as an example for this this leapfrog plot that I showed yesterday, if you had different step sizes, for example, for this orbit, you would still end up with orbits that basically look like circles. Depending on your step size, you might be in slightly different places along the circle, but you would still be lying somewhere in this circle regime. The thing that's really driving these different solutions in this solar system plot is the fact that the system is chaotic. So in this case, having initial conditions for Mercury that vary by less than a millimeter give you extremely different orbits 5 billion years later. So this behavior that we're seeing here is really a result of the chaos of the system, and has less to do with the accuracy of the integrator. So that's one thing that I wanted to sort of emphasize from yesterday. Accuracy matters, but if you have a chaotic system, your orbits are just going to go bonkers, because that's what chaos does. Okay, so that's what I wanted to emphasize from this few body type set of lectures. So I just want to reorient ourselves to the problem at hand today, which is simulating cosmic structure when you have both a sort of like collisionless or nearly collisionless component like dark matter, and when you have a highly collisional component like astrophysical gases. So where we ended yesterday was in this discussion of why you really need to consider these approaches together. Why, when you simulate cosmic structure, it's important to understand the connection between these two components. So we talked about how galaxies live in halos. And so by tracing galaxies, you trace dark matter halos. What I started to want to talk about is a little bit on small scale. So like pushing this galaxy connection to even smaller scales than what we saw in this slice of redshift surveys, so like Sloan and the 2 degree field galaxy redshift survey, but to go to smaller scales than that. And then we're going to come around to somewhat larger scales, and then we're going to talk about the simulations themselves. Okay, so so let me start here. So we have this notion that galaxies live in halos, and in fact that the system is hierarchical, so that large galaxies live in large halos, small galaxies live in small halos. And so if you're a dark matter junkie like me, you want to use the very smallest galaxies to probe as small of dark matter halos as you can, and see if what you find matches with, for example, cold dark matter theory. So what I'm showing here is, again, various of these Aquarius simulated dark matter halos, and I've pasted some dwarf galaxies in this image. So this teeny thing is the Segway 1 dwarf galaxy. It's a galaxy that's about 600 solar masses in stars. Okay, so very few stars. And it's one of the smallest known galaxies. So this galaxy is pretty close to the Milky Way. And in fact, we only are able to detect it because it is so close. And then this here is an image of the Fornax dwarf spheroidal galaxy, which is the largest not disrupting dwarf spheroidal satellite of the Milky Way. And this is an image that I made using data from OSU's Assassin survey. Okay, so a reason to consider galaxies and halos together has to do with this missing satellites problem, which I talked about a bit yesterday, which was basically the observation that if you looked at the number of subhalos around a Milky Way sized host in simulation, here you can see from Ben Moore's simulation, these little knots of dark matter called subhalos, you expect to see a halo, in this case, velocity function instead of mass function in red, compared to the observed number of dwarf galaxies, which is denoted here with these triangle symbols. So trying to figure out what is going on small scales requires both an observational push and a theoretical push. And so a couple of things have happened since this missing satellites problem was formulated about 20 years ago. One is just that there are many more known satellites. So this is an updated velocity function here where we've actually just put in the, this is a plot from a paper that my former student Stacy Kim and I just put out on arXiv in June. But this line here represents an update to this velocity function here with the stellar velocity dispersion on this axis. Many new satellite galaxies of the Milky Way were discovered in Sloan, the Sloan Digital Sky Survey. And actually since the mid-2000s, when Beth Willman and others found the first very faint dwarf galaxies using Sloan, a couple dozen more satellites of the Milky Way have been discovered using, for example, the Dark Energy Survey, even Gaia. There's a nice paper by Torrealba et al. On the discovery of the Aquarius-2 dwarf galaxy with Gaia, and then also with the Hyper Supreme Cam survey and Atlas. So we now know that there are many more satellites. And importantly, another thing that we've learned is that you can only detect a galaxy so far out. So this gray band here represents our best estimated total population of satellites of the Milky Way, based on the fact that we've observed a whole lot more dwarf galaxies. And then in order to extrapolate the whole population from the population of observed satellites, you need to know something about how galaxies might be distributed in the Milky Way halo to extrapolate from 50 kiloparsecs to 300 kiloparsecs. And so that's why there's this huge uncertainty band here, is that we don't actually know, either really on a theory side or the observational side yet, how galaxies are distributed in the halo. And actually part of the reason for the confusion on the theory side is that we still suffer from artificial satellite disruption at the centers of halos. So this is still an active, 20 years after the description of the missing satellites problem, we're still having issues numerically resolving small halos at the center of big halos. And in the past few years, there's been a big push led by people like Frank van den Bosch and his group to really try to understand and make theoretical predictions for the radial distribution of satellites in halos. There's also some very nice work by Han and Frank on this topic. Okay, so, and a cool thing that we can do when we have this new velocity function of Milky Way satellites. Oh.
Sorry to interrupt you. Thanks. On your last slide. I don't know very much about these surveys, but why is it surprising to see dwarf galaxies in the Gaia survey?
So actually it is not surprising, but the thing that is amazing is that this galaxy was discovered in Gaia when it couldn't have been discovered, or it is not as easily discovered in a photometric survey. The reason for this is that the galaxy that Torrealba et al. Found is extraordinarily extended and extremely low surface brightness, which means that the number of stars per square, arc minute, even extremely low. So they were able to identify it as a set of stars that all looked like they belonged to a same stellar population moving together coherently in the sky. So they really needed the velocity information from Gaia to confirm the satellite. But it's an incredibly extended, extraordinarily low surface brightness object. And so it's not a surprise that Gaia found it. It's just showing that Gaia's capability with proper motions is what really helped them find this extraordinarily unusual satellite. Great question. Okay, so one of the things that Stacy and I have been able to do is we have an analytic way of matching to try to make predictions for this velocity function and compare it to this observationally inferred one in gray. Each of these lines is a theoretical prediction which has its basis in simulation. And so we take, so each different line here represents actually the same subhalo mass function. So we're not changing anything about the overall populations of dark matter subhalos. And we're actually applying the same model for relating galaxies to halos. Now, this is also another very active area in simulation work, is to figure out how galaxies inhabit halos on these very small scales. We just took a simulation inspired typical relation and applied it here to make our predictions. And then but the only difference among these predictions is actually the density profile of dark matter halos. Basically, are dark matter halos very dense and cuspy, or do they have more gentle, is the density not rising as quickly in the center? In the case of these orange and blue lines, those are inspired by simulations by Justin Reed and others who looked at the effects of these small galaxies being able to, the baryons in these small galaxies being able to rearrange the dark matter distribution and thus forming sort of like smallish, low density dark matter cores in these halos. The black line is what happens if you assume that the baryons in galaxies are dynamically unimportant, and so that you retain this very cuspy cold dark matter prediction. And so what we find is, based on these simulations that we've now encoded into an analytic model that are best fit for this observed population of satellites of the Milky Way is a model in which you have a cold dark matter like halo mass function, but where baryons are able to move matter around in the inner parts of the more massive of the satellite galaxies, which is represented here by this orange line. And so that's our best fit model for the Milky Way satellite population, is this cold dark matter plus baryon model. And those model choices were informed by simulation. On this right-hand panel, we did something similar for warm dark matter models, which I'll talk about in a bit. Warm dark matter models are models of dark matter where dark matter is born semi-relativistically in the early universe. And so because those particles are moving at high speeds in the early universe, they tend to wash out matter fluctuations on small scales. So as a result, you tend to get a suppressed halo mass function on small scales. And also because halos form later, they tend to be less dense than cold dark matter halos. And here we're in this plot able to show that this velocity function actually is fairly constraining of warm dark matter models. Okay, so this is an example of really trying to understand the dark matter and the baryons together to be able to compare with observations and put constraints on the dark matter model. And where a lot of, again, the constraint comes in part from understanding, in part via simulation, of how the baryons and dark matter co-evolve. Another example of co-evolution has to do with, another example is in the context of self-interacting dark matter models. So in self-interacting dark matter models, dark matter is not collisionless like in the cold WIMP dark matter paradigm, but particles experience frequent, in this case, elastic interactions with other dark matter particles. That leads to energy and momentum transfer. And what it means for the shapes of dark matter halos. So in the top row, we see a galaxy cluster sized halo from a set of simulations that Miguel Rocha and I ran at this point almost a decade ago. And here zoomed in the lower row on the inner regions, is that for cold dark matter halos, which are represented in this left column here, you get these very triaxial halo shapes. And then as you crank up the dark matter cross section, you get rounder halos. And they're not as dense as the cold dark matter ones. So we ran these simulations with only dark matter, no baryons. And one interesting thing that's happened as the simulations that include baryons, i.e. including the hydrodynamics of galaxies, is that you get very different phenomenologies. So this is a plot from a paper by Omid Sami. And here he shows basically sort of what I showed before, but now where they've included baryons. And the important thing to see here is that all these halos look round. So it doesn't matter what the cross section is. Once you put in baryons, you tend to get, in this case, some convergent evolution. And so the baryons in this case are really governing the shapes of the halos. It's not just the dark matter self-interaction that we saw in the dark matter only simulations. Okay, so to understand dark matter, we really need to understand this interplay between galaxies and dark matter, or the baryonic components of galaxies and the dark matter components of galaxies. Okay, so, which is, one of my main points, in my collaborator, Alison Brooks, makes this point pretty much in every talk that I have seen her give. You should definitely check out Alison Brooks and Farah Munshi and Charlotte Christensen's simulations, in particular their recent Justice League and Marvelous Dwarfs simulation series. Okay, so let's talk about approaches then to trying to understand the dark matter baryon connection, and how we can use those, how we can simulate different types of dark matter and then pull dark matter constraints out of a combination of simulations and observations. Okay, so historically, you can classify approaches according to this amazing grid by Mark Vogelsberger and collaborators. I should say that if you're at all more interested in digging into simulations or just are curious, you should really read this paper. This is an excellent, excellent overview of the state of the art of simulations. Okay, and so Mark has classified here, Mark and his collaborators have classified simulation efforts according to this like Mendelian type grid. So in this case, we've got what type of simulation we're doing. Are we really focusing just on a small patch of universe, these zoom in simulations, or a large statistical volume? So this is the difference between understanding individual objects versus ensembles. And then at the top, he separated things into dark matter only simulations versus dark matter and hydro simulations. And as I'll talk about for the rest of this, there are different reasons to choose different of these approaches. So dark matter only large volume simulations tend to be great for large scale structure and are an efficient way of exploring, making predictions for large surveys when you're interested in, figuring out, for example, the 2-point correlation functions of like Milky Way mass galaxies. On the other hand, if you want to understand like how baryons really affect the inner structure of small dark matter halos, you're probably going to want to have a hydro simulation focused on a few systems to really get the resolution you need. So basically, you do the type of simulation you need to do in order to understand the science that you want to understand. But broadly speaking, you live somewhere in this grid. Okay, so let's talk about n-body problems. So I'm first going to consider only these dark matter only type simulations, and I'm going to do that. Oh, does someone have a question?
Yeah, thank you.
Okay.
Are any of these groups considering using quantum computing to increase their computing power?
That's a great question, and one to which I do not know the answer. Yeah, sorry. Yeah, I would just do some Googling or asking around people, who are associated with one of the large simulation groups. What I will say is that there has been some efforts on GPUs, but there are some issues with GPUs that make things challenging. But I don't know about quantum computing. Sorry. Okay, so we're going to consider the dark matter only case, despite what I just told you about baryons being dynamically important. A lot of the important initial work and actually ongoing work is done without baryons. And again, that's because for some of the questions that those groups are wanting to answer, to first order not having baryons in gets you a fair ways. So and also, as we're going to talk about, they're a lot faster to run. So you can build up a lot more statistics a lot faster if you can just not have to deal with those pesky baryons. Okay, so let's consider this left column first, what I will call sort of traditional n-body problems. So again, here I've highlighted in orange what we're going to consider here. These dark matter only zoom or large volume simulations. Okay, so traditionally a lot of work has been done on these big boxes. This is a great set of images where they've highlighted more and more regions in this Millennium N-body simulation. But traditionally, these big boxes have been used to mimic or to interpret wide field galaxy surveys. So if you look at a lot of the interpretation papers for like the Sloan Digital Sky Survey, for example, there were comparisons made to the Millennium simulation in particular. So again, these big box simulations are great for compared to the wide field surveys. Now, sometimes you care a lot about individual types of systems like Milky Ways or individual galaxy clusters. And then it makes sense to really focus in on one small patch of like this volume. So for example, if I wanted to focus on this cluster and really understand that cluster in detail, like its substructure, I might want to run in a Zoom simulation. And what a Zoom simulation means is that you have a much higher resolution in that patch of this box than you do in the rest of the box. And so you really focus all your resolution elements in the place where you really want to understand the system. In this case, like this galaxy cluster. Okay, so why am I talking about big boxes and zoom in simulations? Like, you know, fundamentally, if you have a dark matter particle of say 100 GeV, like, and I have a big patch of universe versus a small patch of universe that I care about, why am I talking about resolution? And what does that mean? And so this is what I mean by resolution. So as I mentioned before, like an individual WIMP might be 100 GeV, or in astronomer units, 10 to the minus 55 solar masses. Okay, now a typical galaxy cluster has, its halo is about 10 to the 15 solar masses. And even like the Segway 1 dwarf galaxy that I showed earlier, that's still maybe 10 to the 8 solar masses, or about, in that case, 10 to the 63 WIMPs. Now, you're not going to simulate the orbits of those WIMPs individually. Instead, what we do is we think about a simulation particle. And when I talk about the resolution of a simulation, what I really mean is how big is that simulation particle compared against like the size of a WIMP. So a simulation particle in like the best zoom in simulations has at the very smallest sort of like 100 solar masses worth of dark matter particles represented by one simulation particle. And so another way of thinking about this is that we're really coarse graining the distribution function. So remember yesterday I told you when you're considering how to run a simulation or how you should think about your problem and methods of solution. When you're in the very high particle limit, you really ought to be thinking about phase space densities rather than individual particles. So when we talk about resolution, we're really talking about how finely are we coarse graining this distribution function. And then ultimately what we're doing in these n-body problems is we are solving a set of Boltzmann-Poisson equations to understand how the distribution function evolves in time. Okay, so I mentioned Boltzmann-Poisson equations. What do I mean by that? So fundamentally, if you have an ensemble of particles that you describe with a phase space density here labeled by F, then the Lagrangian derivative, and here what I mean by Lagrangian derivative is if you were to sit on a particle and follow that particle's trajectory in phase space, or as it moves in space, that the density of particles around it, the phase space density of particles around it, only changes if you have a source term, like you're creating or destroying particles, or if you have scattering. And so that's another way to say, to talk about Liouville's theorem, that if there's no source or sink term for your particles, and if there's no scattering, then you conserve the space density along trajectories. Now you can write down this Lagrangian derivative, like the time derivative for this phase space density in terms of an Eulerian derivative. And an Eulerian derivative is really, in time derivative, is if you're looking at some fixed patch of, some fixed region of space, you're looking at how the phase space density in that fixed space changes. So one way I put it is like, imagine that you're looking at a river and you're sitting on the riverbank. You would think you would use this Eulerian interpretation of the phase space density if you're sitting on the back bank of the river and just watching water flow through like a fishing net or something. You describe the what's going on in the water in that fishing net. That becomes then an Eulerian description, because all you care about is whatever water is in there at some point in time. A Lagrangian description is that if you were sitting on a water molecule and going along the river, then you would be paying attention to what water molecules near you, what they're doing as you're floating along the river. Okay. Okay, I see there's a question in the chat. Go ahead.
Yeah, hi. So in the last slide, when we're talking about, the coarse graining part with the high end, because you have a large number of particles in your system, so we're doing coarse graining. So the question I had about simulation was that, is there a way, to distinguish between different kind of dark matter masses that you're using? I mean, are there any, gravitational effects that arise because, instead of like, 100 matter particle, you could have like very light axions or something. And is there a way to test, the effects of both of these in any simulation or anything?
Yeah, that's a great question. So, so I'm going to break that up into two parts. One is if you have very light particles that are better treated as a field, and where you're really seeing more like wave effects, you have to treat that differently. And I'm going to talk about that in a little bit. If your dark matter is really, best described as particles, you can't tell what the mass of your particles is observationally, unless your particle is so large that it is similar in mass to things like stars. And so that's why there are some dynamical constraints on primordial black holes, for example, that you don't have for much less massive particles. So eventually, if your particle is a lot less than the size of the thing that you're using to set constraints, in this case, stellar dynamics, if your mass is a lot less than that of like a star, basically all particles look the same, whether you have a ton of them, a ton of very low mass particles, or relatively fewer higher mass particles.
Okay, so just maybe a follow-up on this. So I mean, even if you're describing a different set of particles with different masses, so do they, so 100 GeV dark matter mass compared to a 1 keV dark matter mass, I mean, do they have the same equations of motion? Like, do they behave similarly in these simulations?
Yep. Yes. Yeah. That's true. Yeah, that's right. Okay, so yeah, so my mom is German, and there's a saying that at night all cats look gray. And so in simulations, as long as your particle is a lot less than the mass of like a star, in a simulation, all masses of all dark matter particles look the same. So, okay, so, all right. So that's the Boltzmann equation. So that describes the phase space density It's a function of time. Note that there's this gradient of the gravitational potential in here, and that's where things get interesting if you have a system that's not static. So if you've got a halo forming or some other dynamical thing happening with your dark matter, then you need to consider the evolution of the gravitational potential. And here the gravitational potential you can figure out using the Poisson equation, where in this case, this term here is a shorthand for density of massive things. And you can think of it as multiplying for each species of particle you have, you get a different contribution to the density. And the mass density of a species is just the velocity integral over the phase space density times the mass, each particle mass. Okay, so fundamentally the n-body codes solve these two equations together. Okay, so I'm going to talk about cold dark matter first. So cold dark matter is sort of our standard paradigm for dark matter. What I mean by cold dark matter is that it's born non-relativistic. It's stable on cosmic timescales and hardly interacts with anything beyond gravity. So colloquially, people use WIMP and cold dark matter kind of interchangeably, but it's not quite right. Like WIMPs do interact a little bit. As it turns out, not enough for it to matter in any sort of n-body simulation. But then there are other types of cold dark matter like QCD axions. So CDM is not a one-to-one and onto relation with the word WIMP, but sometimes you'll see those were used interchangeably, even though they really shouldn't be. Okay, so for cold dark matter, which is what most people simulate most of the time. Okay, I just lost my cursor. Oh boy. Let's see if I can get it back. I gotta okay, my computer appears to have frozen. Just a second. Hi, sorry about that. My computer just completely froze. All right, so what is the last thing that you remembered hearing me say?
We heard everything. Actually, you said my computer froze and then you disappeared. So after the last second, it was okay. We heard you up to the last second, so it's okay. You can just continue where you said my computer froze.
Sorry, can you say that again? The sound, I couldn't
But we
hear.
heard everything. So
Okay, great.
just continue from where you stopped.
Okay, thank you. All right. Okay, so, all right. So cold dark matter here lies in this huge particle number, extremely high Knudsen number limit. And so what that means is that we are really solving, when we're doing these standard cold dark matter simulations, we're solving the collisionless Boltzmann equation plus the Poisson equation together. Now, so that's great. Okay, and really, as I mentioned before, we're coarse graining phase space density. So what that means is that we have a bunch of simulation particles, and that are simulation particle, it represents basically a patch of phase space. And we're tracking the evolution of that phase space density by following these simulation particles. Okay, so basically what we do is we see where all the other particles are in the simulation, and we compute the gravitational field, all other particles, and we evolve of each particle according to gravitational field from the other particles. Okay, so that's great. So there are two things that we need now that we have thought already, we've screened it, solving the thing now in order to run simulations. One is we need a set of initial conditions, and two is we need some way of tracking the trajectories of all these particles. Okay. Let me just continue.
Yeah, actually, I'm having trouble. The sound is chopped.
Okay. How? Oh.
It's on your side probably because other people on Zoom. Can you hear you well?
Can you hear me better now?
Seems okay now, yes.
Okay.
Try to
So
go on and
just
see.
go ahead. Okay. Two kinds of initial conditions that you can consider. One is we'll call Newtonian initial conditions, and these are the initial conditions phenomenology decoupled from the full cosmic evolution of the system. So one of the exercises that I've put in the folder, which I put in the folder last, how to initial conditions for that. My former student Stacy Kim made.
Not improving.
Okay. Can't play yet.
Maybe. Sorry, maybe you can try to shut off the video and see if the bandwidth is preserved.
Okay, I think I'm not going to play the video, but in any case, I can describe in words that often you want to generate like an equilibrium dark matter halo and smash it at another. In the case that Stacy and I did, and Dave Whitman for these merging cluster simulations. That's what people also do to understand in detail the orbits of subhalos or in bigger systems, in order to get very high resolution. Okay. All right. The other common situation that you find yourself in is wanting to do cosmic simulations. Okay, good. I'm glad it's better. Okay. So simulations, usually we start simulations for cosmological purposes. We start those simulations where linear theory still kind of holds. And then we basically evolve things forward using, in this case, the GR version of the Boltzmann-Poisson equations. So one of the common initial conditions softwares that people use is this one by Oliver Hahn and Tom Abel called Music, but there are a number of other conditions there that you can use. Okay, so those are the initial conditions. So you have to decide if you want to run a staged Newtonian simulation or if you want to run a fully cosmological simulation. Conditions based on which of those camps you fall in. The next thing is that you have special conditions. You now have to evolve your particles, your simulation particles, with the Boltzmann-Poisson equation. equations. And so for this, there are basically two common methods. I should say that there are some novel methods, in part pioneered by Oliver Hahn and Tom Abel to do better. Take a look at a reference document put in Google Drive if you want to learn more about those new types of methods. But for this lecture, I'm going to stick to just the two common methods for solving the Boltzmann-Poisson equations. And both of these exist because these two methods exist because doing direct, like calculating the gravitational force on every simulation particle, every other simulation particle is an n process. So if you have n dark matter particles, the time it takes to compute the gravitational force on each of your particles at each time step scales with n, just computationally inefficient. And it turns out because each simulation particle is not a real particle, but represents a patch of phase space, there are also numerical errors in the full direct summation. There are two ways around it. One is tree code approach. In this case, you group particles together into this tree-like structure. And you calculate the gravitational force on each particle by calculating the force from the particles in each one of these boxes. This is a method pioneered by Barnes and Hutt. There have since been, bells and whistles added to it. But this way of computing the gravitational force on each particle scales as, or on all your particle scales as log n. So it's much, much faster than doing direct summation. The other method is to basically slap down a grid, see where your particles lie in this grid, and do basically an F on the density field, or to find the gravitational field, and then take a derivative of this potential to get the gravitational force. So this is, so whereas this tree is a grid-less code, even though you can kind of see a grid, it's a grid that sort of changes with time and it's dynamic. It's fundamentally a different approach to calculating gravitational forces than by basically FFTing your way to and then taking a gradient of it. So this is a summary table from that great review article by Vogelsberger et al. To see what different of these big code packages use. So these are some of the code families. See that a lot of these codes are public, so you download these codes and play with them. And that is for tomorrow is actually that they deploy a hybrid approach. So using a tree code for sort of smaller scales, and then they do much approach for the larger scale. Okay. Hopefully you guys can hear. I'm just gonna keep talking. Unfortunately, our Wi-Fi is what it is.
Can I ask a quick question?
Yeah.
I don't know if you can hear me on. Okay, great. Thanks. So from my understanding, the purpose of these different approaches is to kind of maximize what you can do with the computing power you have. So this might be a naive question, but why would the community just kind of get together, pick one code and run it for like a long time to get some kind of extremely precise result rather than doing these kind of complicated methods to maximize computing power or maximize what you can do with computing power?
So that is an interesting question. And part of the issue is that people have different science goals. And so, the simulation you run for one type of science goal is not running for higher and higher resolution. And so you really need efficient algorithms. If what you care about is resolution, you need efficient algorithms in order to get answers on any feasible timescales. Like currently, the biggest simulations cost somewhere between 10 to the 7 and 10 to the 8 CPU hours. And that's just a lot. So really the goal is to make your algorithms as efficient as possible for the computer architecture that you have available to you. Okay, so there are a couple of things that are good to check. One is it's always a good test especially when using new codes for the start with this where you know the answer to and just let it evolve. So something that we commonly do is start with an equilibrium halo and just evolve it. Another thing is that even if you start out with identical initial conditions, if you change something about your algorithm or of the density field in the same patch of space, you're going to get a somewhat different answer. And that's just because of chaos. And so in this set of Milky Way analogs in the Elvis simulation that my collaborators ran at UC Irvine, they had one halo called Hera that they then evolved at higher resolution. And one thing that's different between the standard resolution and the high resolution is that one of them had like a large Magellanic cloud inside the virial radius and the other didn't. And the fact that there was one and not the other was a result of numerical chaos. The other simulation did have a large Magellanic cloud, but it was just outside the virial radius. So basically what you should expect is the statistical properties of your systems to converge, but not the exact properties of the systems to converge. Okay, so that was cold dark matter. I want to talk a little bit about not cold dark matter. So let me talk about warm dark matter first. So this goes to the question that someone asked earlier about whether you use the same methods for particles of different masses if you get the same answer. You get different analogy of halos for different particle masses. Not the algorithms that you use are different or not. So for warm dark matter simulations, we use the same methods as cold dark matter. The issue is that your initial conditions are different. So for warm dark matter models, for these typically light particles that are sort of born semi-relativistically, you get a suppression of the power spectrum because particles are flying out of small overdensities. Look at enhanced particle velocities compared to the CDM case. And so this is a plot I pulled from Mark Lovell's simulation where he shows one particular warm dark matter model. And this is sort of a Milky Way mass halo realization. And then you've got this plot from Springel et al., which is this other, this is a cold dark matter Milky Way simulation. And you can see a difference in structure, and that structure is different because of the initial conditions, not because of the methods. Okay, so warm dark matter, same methods you use for cold dark matter, it's just different initial conditions lead you to a different outcome. One thing that's important for warm dark matter simulations is that you do get artifacts or rather you can get artifacts, depending on actually the details of your gravity solver on small scales. Left-hand panel shows particles end up at redshift 0. Or skip out basically because if you do direct summation and you actually have like two-body gravitational scattering of particles in here, you can have basically Poisson fluctuations artificial helium. You don't have that problem with cold dark matter simulation. So you don't get these halos and CDMs and just beware of that. Okay, sorry about the sound. Okay. So let me talk about self-interacting dark matter. In this case, we're solving an equation, which is annoying because it's also not in the hydro limit. So the key thing for self-interacting dark matter simulations is that when your coarse grain space density, you have to think really carefully about what scattering actually means for coarse grain particles rather than your fundamental particles. So the thing that matters for self-interacting dark matter simulations is getting the momentum and energy transfer right. And so the various algorithms that exist are designed to get the energy and momentum transfer right, not necessarily the physical details of scattering. So this is pulled from a very nice paper by Felix Höfer and collaborators, where he shows what the scattering looks like in the versus the center of mass frame. Data in the center of mass frame can be large, often approach to figuring out the momentum and energy transfer than if you have a cross section which is really dominated by small angle scattering. Okay, so there are a bunch of papers, including mine, on algorithms. I would say point you to papers by these people like Andrew Robertson, Orca Banerjee, Felix Kalhofer, and pretty soon a paper comes my student Carton Zhang on how to think about these scattering algorithms for different microphysical models of dark matter. One of the hard is self-interacting cross. So by core collapse is initially when you turn a low density core, which is represented here by these lower lines. Okay, so this is the density on this axis, the function of distance from the halo, and then the time axis goes that way. But if your cross section is large, then on even Hubble timescales, your halo becomes unstable and you get initially described for blockbusters, is that these and densities. Basically, what's going on here is initially you're infrequent scattering regime over here, but by the time
You think we should stop or?
Yeah, it's hard to understand. It's hard to follow.
Maybe we'll ask her if tomorrow she has 20 extra minutes to spare. Can you hear us, Annika? So
Okay.
here the sound is really bad, and in the last few minutes we couldn't really understand.
okay,
Maybe it's better. Do you have any suggestion, or maybe we just stop here for today and we start from here
So-
with next 15 minutes or so tomorrow?
I just switched to a different Wi-Fi signal. Is this better or is it about as bad?
Now it seems okay. Yes, let's try it and see. We'll let you know in the chat if it gets better again.
Okay, I'm really sorry. This has been a sort of persistent problem throughout the pandemic that most of the time the internet is fine, but sometimes it just flames. And I'm sorry that this morning is a flame time. Okay, so self-interacting dark matter can be challenging through this collapse phase because you really transition between several scattering regimes. And one thing that is a problem, well, when you go to these high densities and when you're in the fluid regime, is that you have to take very, very, very small time steps to resolve the phenomenology. And so that ends up being the thing that really makes actually hydrodynamic simulations so costly, as well as these core collapse simulations, is that when you have high densities, you have to take very small time steps because the dynamical time, the typical time scale for particles to move in the system becomes very, very small. Okay, so finally, let me talk about fuzzy dark matter or wave dark matter. So these are cases where the occupancy of states is extremely high. And so it makes more sense to talk about dark matter as being wave-like than particle-like. And so you get extremely different phenomenology, and typically the simulation methods are different for this type of dark matter than for the more particle-like dark matter. So one of the things that you see here is like a solitonic core. And then these ripples in the density field are basically time-changing ripples, basically interference effects for your wave-like dark matter. And there's a whole literature on simulation approaches to fuzzy dark matter. I've put a bunch of links in the reference document if you're really interested in nerding out over different algorithms. This again is a very active field where people are thinking about new and better algorithms for simulating fuzzy dark matter. All right, how's the sound been going the last couple minutes? Is it better?
Yeah, it's perfect now. Very good.
Okay. Okay, good. All right, so I think at this point I'm going to skip over a cool thing and maybe get to it tomorrow if people are interested. But instead of this, I'm going to talk a bit about hydrodynamics. Let me ask, are there questions about the n-body problems, like simulating different types of dark matter?
One question here.
Okay.
A second.
You said that we need to resolve Marla, did you hear me?
I can't hear you, sorry.
You said that we need to solve the Blasov equation
I would like to know which kind of method do you use, and in terms of it's more efficient to solve because we can solve the last of equation in terms of the hierarchy equations, and I would like to know more about that and which kind of methods do you use, and if it's more efficient to solve the rest of the questions in terms of answering the couple of questions that has a hierarchy, and how do you close the hierarchy in that case?
You mean, okay, so the question is how to deal with the hierarchy of scales in a problem? Is that?
Okay, so maybe I was not clear. I mean, to solve the last of the question, it's equivalent to solve a system of answering the couple hierarchy of the questions for the cumulants for the distribution function. Okay. And I would like to know if it's more efficient to solve this problem in terms of find something to close the hierarchy, or how do you close this?
Oh, how to close the hierarchy?
Yeah, or how do you solve the last equation? I mean, which is the more efficient way to solve this equation?
So typically for these simulations, there's some scale below which we just can't resolve. Sort of having to do approximately, you know, on the scale of individual particles. So we can't resolve things on such small scales. So that's, one can think of it as sort of like that being sort of the coarse graining limit. I'm not sure if I'm exactly answering your question, but on larger scales, we solve the Vlasov equation by, you know, in the case of the more particle-like framework, essentially following around the individual particles in the simulation, the individual simulation particles. But I'm not sure if that's exactly answering your question.
We can move on, I guess.
Okay. All right, so, okay, so I want to mention just a little bit about hydrodynamics. So once you move beyond dark matter, even if you have like self-interacting dark matter or fuzzy dark matter, things get really complicated really fast. And the reason that you should care about this is that, you know, for me, so this is a plot from a paper by Risa Wexler and Jeremy Tinker. For large halo scales, we have a very good understanding of how galaxies and halos, this is the stellar mass of the galaxy over the halo mass, but we have a very good understanding, both observationally and in simulations, of how galaxies inhabit halos. But on these small scales, which is usually what's of interest if you are someone who thinks a lot about warm dark matter or self-interacting dark matter or fuzzy dark matter, the relationship between dark matter halos and their galaxies is not well understood. But also take a look at how few baryons, how few stars there are per unit halo mass. It turns out that even a small amount of baryons can wreak havoc on the shape of your density profile. This plot to the right is a plot from a paper by Fabio Governato and his group at the University of Washington. And what they show is compared to a cold dark matter only simulation, which is this black dotted dot dash line here, the density profile of this dwarf galaxy's dark matter halo changes dramatically with time as baryons cycle in and out of this galaxy, even though overall, there are very few baryons in this halo at any given time. And so you can see this when you look at the blowout of gas from a dark matter halo, here represented in density and here in temperature. that when you have stars forming in these small halos, the stars blow out massive amounts of gas and they tend to entrain dark matter gravitationally with them. And so if you really want to understand small scale structure problems, you have to understand how galaxies inhabit halos and then how that small bit of baryon messes up your dark matter distribution. Another thing that's pretty interesting is that, so I talked about galaxies as being sort of a nuisance for understanding dark matter, but conversely, dark matter physics can really affect the star formation properties of the halo. So this is a plot and a table from a paper by Akasha Cruz, who's a grad student at the University of Washington. And what she's shown is that in self-interacting dark matter cosmologies, you actually get very different star formation histories. Here, the thing to look at is the cold dark matter version of the star formation history of this galaxy is represented in solid lines, and dashed lines is with self-interacting dark matter cosmology. And the reason for this basically has to do with how black holes in galaxies move around the galaxy during mergers. And so black holes are much less efficient at getting to the center of a self-interacting dark matter halo than in a cold dark matter halo. And that actually suppresses then the effects of the black hole on regulating star formation. So in her papers, she's shown that you get enhanced star formation in Milky Way-like galaxies for self-interacting dark matter cosmologies. So that's, if you're a galaxy person, that is an interesting thing. And if you're a dark matter person, that's potentially a signature of self-interacting dark matter. Okay, so you really got to understand what's going on with the gas in galaxies on a surprisingly large range of halo scales in order to make predictions for galaxies and constrain dark matter physics with galaxies. I'm going to skip that. And so what that means is that you really have to understand astrophysical gases, which are in this very small Knudsen number limit. So basically, if you want to consider then all the physics that has to go into this galaxy, there's a formation, take a look at this, again, this review article by Mark Vogelsberger, but you've got to be able to cool gas, you've got to properly model the interstellar medium, you've got to be able to form stars, destroy stars. There are a lot of baryonic components of a galaxy that have to be modeled. And one thing that's important to note is that we don't have an ab initio first principles model, for example, for star formation. And so every different code has a slightly different recipe for some of these bits of physics for which there are no ab initio type models. Okay, so there's a lot going on. And fundamentally, you have to solve a set of hydro equations for each of these components of the galaxy. So, and the set of equations that you solve depends on what is your method for solving the hydro equations. Okay, and another thing I'll note is that these hydro equations, in this case for gas, these are basically moments of the fully collisional Boltzmann equation. So if you want to get these equations from the Boltzmann equation, you basically just slap some integrals on it, various moment integrals on it to get there. Okay, so there are basically two very common approaches and a third becoming more common approach to solving the hydro equations. One, again, is a set of gridless methods, the most common of which is the smooth particle hydrodynamics approach, where you basically view each simulation particle as sort of like a tracer. And then you figure out different hydrodynamic quantities by basically putting some kind of smoothing kernel on each simulation particle and summing up contributions from all sorts of particles. This actually also, this approach underlies the guts of Stacy, Kim, and my self-interacting dark matter code. We borrowed from the smooth particle hydrodynamics framework. So that's the most common gridless method. And I put some very nice references to this method in that big reference document on Google Drive. The other common approach is a grid method, where basically you just lay down a grid. This is, again, like you're sitting on a riverbank and, you know, gridding up the river in front of you. Very commonly, there's an adaptive gridding that can happen. And what these grid methods are really good at is doing things like resolving shocks. So you can very finely resolve shocks that are just harder to do in the smooth particle hydrodynamics approach. Okay. And then the newest thing that's been gaining in steam in the past 10 years is this hybrid approach, where you have some aspects of the smooth particle hydrodynamics, this Lagrangian following tracer particles as they move approach, and then this grid-based approach, this Eulerian approach. So, these, the two most recognizable codes that use this approach are the Arepo code by Volker Springel and the Gizmo code by Phil Hopkins. So this is on the left an example of this moving mesh from Volker's paper. And then on the right is an example of how these moving meshes do and the scales that you can resolve with respect to a fixed mesh problem. And this is a standard Kelvin-Helmholtz instability type test here. Okay, so you can resolve a lot more detail and structure in this moving mesh approach. Okay, so let's see what codes actually use. So you can see that there is a diversity of approaches here. So as I mentioned before, Arepo and Gizmo are these moving mesh type codes. Probably the most famous adaptive mesh refinement code, or these mesh codes, is Enzo. One thing I'll point out about Enzo is that it has a huge community development base. And so if you go to this website, you'll find all sorts of community packages for it. They now have a fuzzy dark matter package, which is super cool. And another thing I'll say is that Gadget is this, this SPH code originally written by Volker Springel, but since this paper came out, there's been a new version of Gadget called Gadget4, which is now public. And so it supersedes Gadget 2 and 3. Okay, but there are tons of different codes and most of them are public. So you can just download them and use them yourself if you want. And again, these different codes have somewhat different prescriptions for all these bits of physics, and it can lead to some interesting consequences. Okay, so let's put it together and see what happens. There are a couple of words of wisdom I want to point out before we end in 5 minutes. Okay, so if you're interested in simulations, do not write your own code from scratch. Instead, download one of these public codes and just play with it yourself. You'll also probably need an analysis package because, you know, basically a simulation will generate data for you, but then you got to do data analysis. And there are good public analysis packages as well, or you can, it's in some cases not too bad to write your own, although do not write your own Halo Finder. Another thing that you could do if you don't want to run the code to get data yourself, but just want to analyze some data, is to start with a public simulation data product and go from there. So again, I would recommend downloading one of these and just playing with it if that sounds interesting to you. Note that there are many different flavors of these codes. The public version is not going to have all the bells and whistles that some of the others do. It's just that, there are many versions of a lot of codes. And the public version tends to be just one instance of the code. One of the things that you will probably need is a Halo finder. Again, I would recommend not writing your own, but using one of the publicly available ones. There are a lot of great papers written on testing the strengths and weaknesses of the different Halo finders and other pieces of analysis code. And so if you're interested in that, just check them out. And then there are other public visualization tools, which I just throw in here for your reference. Interestingly, there have been a lot of comparison projects. So I mentioned the Halo finders before, but as I also mentioned before, there are a bunch of different recipes for the hydrophysics. And one important thing that's happened is this Aug4 project to basically compare all these different codes against each other. In this case, they are running Milky Ways with as close to identical physics and as close to identical initial conditions as they can. And as you can see, the gas temperature maps look pretty different for these different codes. So if you're interested in that, please check out this paper. Okay, and then if you just want to play with simulation data and don't want to run code yourself, you're in luck because there are lots and lots of simulations that other people have run, and a number of these have public data products. So my group in particular has used the data products from the Illustris and Illustris TNG simulation suites. They have a very nice website. My student, Chris Garling, has used those data to basically figure out quenching mechanisms for some small dwarf galaxies orbiting low mass halos. And so anyways, it's great. The Millennium Project is another very famous simulation project that has a database with an SQL interface where you can sort of query the system and study objects that are interesting to you. I'm not going to have time to talk about semi-analytic modeling, but it is another approach, or semi-empirical modeling. But these are other approaches of modeling the connections between galaxies and halos that don't rely on the full simulation, hydro simulations, but instead have simpler recipes or prescriptions for matching galaxies with halos and their co-evolution. So if you're interested in these, check out these references and the other references in my document. But my group has been working with Andrew Benson's group and observer groups to actually deploy this methodology for studying dark matter physics in the context of strong gravitational lenses. Okay, so I'm going to end here for today, and then we'll talk tomorrow about what we want to do tomorrow. But simulations are really powerful tools for revealing complex physics on small scales, either dark matter physics on small scales or baryonic physics. There's a lot that goes into these simulations and the design of the simulation for the science question of your choice. And if any of this sounds interesting to you, the best way to get into it is to just either start simulating something or downloading some simulation data and just playing with it. So it's your sandbox. All right, I will end there for today.
There is any last question here in Zoom or Zoom? Okay, so thanks. See you tomorrow, Annika.
Okay, have a wonderful rest of your day.
Oh, about the.
No, I'm good. That's my first.